So the next question is can we trust the model, or to rephrase, can we use the model? Is it statistically significant from just using the average y as our estimate? So for this, we can use the F-statistic, and the F-statistic is a measure of the overall explanatory power of a multiple regression model. So for example, you have the model, you have y equals to the intercept, the population intercept, the beta naught, and the beta 1 is the first slope, and then you have several, let's see, 2x2, then you have several slopes because you have included k different explanatory variables. So k is the number of explanatory variables you include in your model. Epsilon is like a bucket of all the other explanatory variables which have an effect on y, but you did not include. And so k is the number of x's, and n equals the number of observations. So what you know, or let's take the null hypothesis first. The null hypothesis for the F-statistic is that all these slopes, not the intercept, but all these slopes, beta 1 equals to beta 2 equals to beta k equal to 0. So the null hypothesis is that all slopes are equal to 0, or not different from 0, not statistically different from 0. And in that case, you can use the intercept as your model. Okay, and the alternative hypothesis is that beta 1, or let's say it like this. The alternative hypothesis is that at least 1 beta is different from 0. Okay, so you at least have one significant slope. Okay, and how do you calculate this F-statistic? Well, you have this equation, and this is a constant, because you know this when you think about what kind of model you are going to estimate. You know this. You know how many observations you have. You know how many x variables you have, your explanatory variables. So this is really a constant. And after you have estimated your model, you get the r squared, which is the portion of variance in y, which is explained by model. Okay, and then 1 minus r is the unexplained variance of y. Okay, so the F statistic is really a ratio of the explained variance divided by the unexplained variance. So the more you can explain, the higher the F statistic. Okay, which means that the F statistic is really like this. The F distribution is really like this, and you get like an F statistic, okay, and this would then be the p-value, and the p-value is the probability of getting a more extreme F statistic by chance. Okay, and of course software is calculating this. So let's see one example. Okay, so we have the Starbucks multiple regression. We have two x variables, okay, and we have sales per square meter, and we have 65 observations, and given the r squared, you could calculate the F statistic yourself, but of course the program does it for us. This is the F. This is the F statistic. Okay, so it's 45.49, and remember that we have to look at the p-value. So this is the p-value. Okay, so the p-value tells us that if we want to look at the graphics of it, the F distribution, then it looks kind of like this. It's always positive, and what we have here is the probability of getting a more extreme result by chance, and the probability of getting a more extreme result by chance is virtually zero. Okay, it's incredibly close to zero. Okay, you see that here, which means that we reject the H naught. Like let's see, where can I H naught of beta 1 equals to beta 2 equals to 0. We reject the hypothesis that both of these slopes, population slopes, are equal to 0. Okay. And so the question here is, does the model have explanatory power? We can say yes, because even at 1% level, we reject H0. Okay. So, and the second question is median income statistically significant determinant of sales per square meter? Okay, so median income is here. Okay, so the coefficient is 85.74, and with a standard error of 9.02, which gives us a t-statistic, which tells us that the coefficient for median income, it's 9.5 standard errors away from 0, which gives us the probability of getting a more extreme outcome than this is virtually or it's close to 0. Okay, because what we have found is that if we look at the distribution of the coefficient, it's assumed to be normal distributed. Okay, and we have found a value of 85.74 or 75, and we have negative 85.75 because this is a two-sided test. If you look here, what is the probability of getting a t-value greater in absolute values? In absolute values from 0, and the weight or the area or the probability in the tails are virtually 0. Okay, for any practical purposes. So, is median income statistically significant determinant of sales per square meter? Yeah. So we can say that the p value is very close to 0, which is lower than 0.01. Here we use the 1% significance level. We could also use the 0.05, the 5% significance level, and the p-value is so low that we have to answer yes to this and yes to this. Okay, so that's an example of how you can interpret the output from a statistical program, and if we put this into practice, you have learned how to read the multiple regression output. You look at the F-statistic, the p-value for the F-statistic, and then you look at the p-values for the different coefficients in the model, and you interpret them. Okay, so you check the overall F-statistic before you look at the t-statistics, because if the F-statistic is not significant, then you have to remodel. you have to remodel. You have to build a new model, which might be significant. Okay, and for example, what makes a variable important? Well, you have two kinds of significance. You have the statistical significance, in which you look at the p-values of the coefficients. Okay, so if the p-value is really low, then you know that the chance of getting your result, or more extreme, is very low. Okay, but you also have economic significance, because if you have statistical significance, it might just mean that you have a lot of data. Okay, so if you have a lot of data, even tiny effects from the explanatory variable onto the response variable might be significant. So you have to look at the economic significance, and then you look at the size of the coefficients. So here you can think, how can I use this in practice? Does it matter? Okay, for example, if you make a model to forecast stock prices for the next day, but you have so much data that the model is significant, and the slopes, they are significant, but the size of the coefficient is so small that you can't really use this model, because when you try to trade based on the model, your profit is eaten up by the bid-ask spread, or the fee to the broker. Okay, so you have to look at both statistical significance and economic significance. And the partial slopes, they are the B's. Okay, and you have to look at what kind of interpretation do you, how can I say this? Okay, how can you think about the partial slopes? Okay, because if y is measured in kroners per square meter, and for example, x1 is measured in kroners, okay, then the b is measured in like units per square meter, right? Okay, so you have to think about what is the effect of a change in x change. Okay, I can write it. Let's see. Let's see. We can say effect of change in x on y. So what is the effect of a change in x on y? Okay, that's really the key to interpret these partial slopes. And whenever you do that, you are inevitably holding other factors, all the other x's, you hold them fixed. Okay. And even if you get a high r squared, does not mean causality. The causality can go both ways, and there might be other confounding variables, which is included in the error term, which you included in the error term. Okay, so of course we all like a recipe. So these are the main steps in fitting a multiple regression, and actually you're kind of lucky, because you don't need to gather data, and you don't need to clean data, and like gathering, like step 0, gathering, cleaning, and organizing data is often the most time consuming. Okay, so for example, if you were told that, well, you're working as a data scientist, and you're told that can you find the factors or the variables which affect the survival of cancer patients, then you would spend a lot of time gathering, cleaning, and organizing data. Okay, because if your boss had all the data, then it was cleaned and it was organized, then it would be super simple for your boss to just do the analysis. Okay, so what you have to think about is what problem are you trying to solve? Okay, and what kind of data do you need? And for example, do you have any confounding factors? Okay, maybe you are running a regression, and you wonder, okay, what kind of other factors might explain my response variable? Okay, and of course, scatter plots. Check scatter plots versus each of the x, and identify outliers and curved patterns. And now you know what to do with curved patterns. Okay, and if all the x's appear linear, like y on xi, then you can fit like a linear regression. Okay, and this might be the y versus like xi. Of course, it's difficult to plot the multiple regression model, because you have so many dimensions, often so many x's, and but what you can do is that you obtain the residuals and the fitted values, and then you can make scatter plots. Okay, and let's see, scatter plots of E here versus for example y hat, scatter plots of y versus y hat and E versus y hat. Like y versus y hat should be like this upward sloping. They should ideally be on a line, whereas the error on y hat should really be focused on 0, and the variance should appear constant. Okay, and you can check the residuals for dependence, and if you have a time series data, like then here you plot the residuals on each of the axes, and if you have time series data, then you can check the correlation of the error at time t on the error at the previous time slot. Okay, so that would be t minus 1. For example, t measured in days, then you have the error for 1 day correlated with the errors on the day before. Okay, and for this you can use the Durbin-Watson test. Of autocorrelation. Okay, so you plot residuals on each x, and you find no patterns, hopefully, and if the residuals are normal, then you check that with a histogram. Okay, and if they are basically normal, then you can make like prediction intervals by using the estimated y and the standard error or standard deviation of the errors. Okay, to get like the 95% prediction interval. Okay, and of course you have to use the F-stat to test the null hypothesis that the model has no explanatory power, because if the F-stat fails to reject the null hypothesis of at least one significant slope, then the model is not significant, and you have to think again about what kind of problem you are trying to solve, and include relevant x variables. Maybe you have forgotten an x variable which is quite important to explain the y variable. Okay, so if the test for the overall model is significant, then you can test and interpret individual slopes, the b's or not the p's. That's the b's, and you look at the p values. Okay. And then you can just check if there is statistical significance of the slopes, and if any of them are economic significant. So, see you next time.